And for recording purposes, I'm gonna say basically everything we talked about again really quickly. So then when I do call you, please do not say what, because I'm literally re-explaining it again. Okay, so we have a bunch of equations here. We want to know what expression can be really any sort of like mathematical statement, like numbers, variables, maybe both. Into A, what can we plug into A to make it true for all values of X? So we mentioned that the answer for number 1 is that A has to be X. Because now when I plug it in, that's what substituting means, like when you plug in that number, substitute it in, I now get something that is true. X squared is equivalent to X squared. And that's all we're really looking for this. Table 4, what does A have to be in number 2? To make it true. 3X. Okay, so anytime you plug stuff in, do use parentheses. Although sometimes the parentheses don't necessarily change the order of anything in that problem, like in the first one when we plugged it in. Still, the only operation is v squaring x. But when I use it here, it's exactly like the other side, completely identical. Doesn't change any sort of like operation thing, but anytime you plug stuff in anywhere, always use parentheses. Table 5, for the next one, what does A have to be to make it true? Okay, let's see, if I do plug it in to A, would that be the same as multiplying 7x by 7x? So let's address that. Anyone else at table 5 think they know it? Whatever we put over here for the A, so this is where the A was attached to this exponent, it needs to mean the same thing as 7x times 7x. Okay. 14x squared would actually be, and I don't know what 14 times 14 is, so let me double check. 14x, and then you square it, would be 196x squared. So that's definitely not 7x times 7x. Anyone else in the class think they know the answer for number 7x. If I make the A 7x, and if I simplified it, it would give me the same answer. But exponents tell you to multiply the base by itself that many times, right? So this is like the expanded form of this. All right, but if you did solve it, 7x times 7x is 49x squared. If you simplify both sides, you would get the same answer. So they are equivalent, and A is 7x. Okay. Let's see, table 6. What about the last one? What does A have to be in the last one? Okay, let's see. So on the left side, it was this. If I plug in A, I'm going to use parentheses because that's what you're supposed to do when you plug stuff in. Would I still be following like the same order of operations? So like order of operation, pandas, parentheses, exponents, multiplying, dividing, addition, subtracting. You actually would. But this one's a common mistake, but like just think about it. In the first one here, according to order of operations, I would square the x first and then multiply it by 25. The way that it's expressed over here, I'd be multiplying by 25 and then raising it to the power of 2. So that's going to be a completely different answer. And you do test it out, like you could plug in numbers for X, it wouldn't be equal on both sides. So try that again, and that's a common mistake, like my first hour said the same thing. What would give me 25x squared? 5x, and then b squared, like this. So if I make the a 5x, and then it's squared, 5x times 5x is 25x. So now if you make a just 5x, now it works. This, you could show this way. You could apply your exponent rule, if you remember it, the power rule, where like you distribute the exponent to things being multiplied together inside or divided inside. It doesn't work if it's like adding or subtracting inside the print. So you'll see that later, but if I were applying my power rule, 5 squared is 25, and then x squared, so like, there's other ways to prove that they're equivalent, but that's what it has to be. Okay, questions on that? All right, so anytime you square something, and it could be anything, it could be a variable, it could be an expression, it could be just a number. But then we refer to that as a perfect square. And that's the title of today's lesson, lesson 11, what are perfect squares? So the goal is to see how perfect squares make some equations easier to solve. So really, technically, all of these you could probably solve using the other methods we've already taught you, but you'll see if you can recognize that there's perfect squares on each side, then it will take you some steps. And of course, this is going to also lead into the next couple lessons. So you need to be able to identify perfect squares, whether it's in standard form, factor form, vertex form. You'll be tested on that directly. It'll say which of these are perfect squares. You'll have to figure it out. And then recognize that quadratic equations that have perfect square expressions, be able to solve them. I record every day, as I am right now. The puzzle piece, I didn't like snip a picture of it, but it's unit 7, lesson 11, so it's already in there for the beginning of the week. Your next quiz will probably be next week, so just be ready. I don't know when exactly, but it'll start from lesson 9 and beyond, so whatever we're covering right now. Really no room for procrastination anymore. So any questions? Okay. So moving on. These are written as a product of factors. So these would be like the answers to a multiplication problem, or like before you multiply it. You need to be able to write equivalent expressions in standard form. So when something is in standard form, it is what? How can I tell if it's in standard form? It's fully simplified. So like nothing more to multiply. We can still multiply in that problem that it's not in standard form yet. Fully simplified, and then technically it should also be in order of descending exponents. So if there is an x squared and an x term and a constant, write it in this order. All right, but do that for each of these. Especially these ones were a unit 6 skill. So just, you know, remember what we learned, because that's really how you'll kind of check your answers. I'll give you 5 minutes to multiply all of these into standard form. What is in parentheses 3x squared? Or what's the standard form equivalent is what it asks, but to get to standard form, you're really just multiplying. So what is 3x squared equal? Okay, class, we agree? This is just multiplying, so I don't know why I don't have like more people answering me right now. Is this correct? Does this equal 9x? It should be 9x squared. All right, because exponents tell you to multiply the base by itself. The base right now is 3x, so it's like doing 3x times 3x and multiply the coefficients like normal. Apply the product rule on your variables. Adriana, what's 7x times 7x? Compare that to the first one and maybe adjust your answer a little bit. We're missing what's x times x. Okay, good. The only time you guys should ever be like multiplying something and getting that same number or same letter is if you're multiplying by 1. So like, that's a common mistake too. People will put x times x and say that it's still x. Like, no, it should definitely change and it's x times x is x squared. Table 8, what about the standard form for part C? What is it? All right, class, any disagreements on that? So that we did in unit 6. You could FOIL, you could double distribute, you could box method. If I FOIL, I like FOILing, it's like less messy. So multiply the first terms, we get x squared. Multiply the outer terms, we get x times 4, which is 4x. Multiply your inner terms, 4 times x is 4x. And then multiply your last terms, 4 times 4 is 16. However, standard form is fully simplified, so any like terms, you combine them, so this is correct. Once we combine the 4x and the 4x, we get 8x. Now, table 9, what is the standard form of part D? Okay, I heard x squared, anything else? 1x squared. Anything else? No. Okay, so we got part of it. That's if I multiply my first terms together. All right, so what I mentioned earlier is you can't just distribute the exponents like in the warm-up. The only reason that worked for the power rule down here is because they were being multiplied together, like the 5 times x. And can distribute the exponent. Only works if inside is multiplication or division. When it's adding or subtracting, that doesn't work. Like you can't just make it, and even then, like that wouldn't have equaled this necessarily. You can't just like make it x squared plus 1. You're completely forgetting like that middle term. So you have to expand it first. Exponents tell you to multiply the base by itself. And then from there, you could FOIL, double distribute, box method, whatever you like better. Table 9, can you finish it now then? Now that I've expanded it, can you tell me what I get from FOILing? Okay, good. And then if you just combine like terms, let me move this over. I wasn't sure if you're gonna give me the final answer or like before we simplify. But when you combine like terms, it then becomes x squared plus 2x plus 1. And this is our single one. All right, good. Questions on that? So then table 1, what is my standard form of part E?
X minus 7. And then X minus, Oh, wait, standard form?
So it sounded like you were expanding it first, which would be like
Oh,
your
I know
first
this
step.
one. I know.
Okay, so what's my final answer?
X squared minus 7x minus 7x plus 49.
Okay, so this is what you get from multiplying this part out. Technically not standard form until you simplify it, so like combine any like terms. And then my final answer in standard form is. I like terms, do I have any like terms? So combine them to get x squared,
So this becomes 45. There's no x squared minus x.
minus 14x, and then plus 49. Because -7 plus a -7, and these are the like terms that I was talking about, give me a -14. If you remember, like the difference of squares, that one where like the signs were opposite, that's where you have like your middle terms cancel out. But these are the exact same, so I should expect a trinomial when I'm done, okay? All right, last one with the letters, table 2, what do you get for your standard form? I don't even like the music home from our lesson. This is like refreshing your memory on a unit 6 still. Which you still need for this unit because it all repeats, they're also about quadratics. We did 2 examples, just like this one. Although now there's another variable involved, it shouldn't really change anything. I like the standard if you have it.
X squared is x squared.
Okay, almost completely right. Okay, 2xn in the middle. Or usually we put it in alphabetical order. Although 2xn and 2nx would be the same. Usually we put it in alphabetical order. But now this would be the right answer, so good. So then first you would have had to expand it. Then FOIL, or whatever you like better. When I multiply my outer terms, I get nx. When I multiply my inner terms, I get nx. When I multiply my last terms, I get n squared. Now, this is really interesting. Like, do you notice any patterns when we got to this stage between combining the x terms? Like, what are we noticing for each of these? So yes, we do combine like terms. What are we noticing about the like terms in each of these situations? Okay. What I'm looking for, there is an X in each of them. But just look at it. What are we noticing in each situation? And what I'm asking you is really like not that complex. Harley? So in each situation, the like terms that we happened to combine were the same. It was 4x plus 4x, or it was 1x plus 1x, or it was -7x plus -7x. Even down here. And while you might have written xn for one of them, it's still like the same thing being added. So that's really characteristic of perfect squares. All of these are examples of perfect squares. Because if you multiply anything by itself, that's considered a perfect square. But these especially, I mean, you can probably tell that they're perfect squares when they're in factor form. But on your test, you're gonna have them in standard form too. Now, personally, like I prefer to memorize fewer things. Like for me, I would just factor it and then see, like, is it the same exact parentheses being multiplied together? So I would recommend that for your studying purposes. But other teachers will teach it as you can recognize perfect square trinomials from the standard form if they follow this format. Where I have a perfect square here at the first term, a perfect square at the last term. And then that middle term are like usually like our linear term, we call it, is 2 times the square roots of your first and your last term, which is true. What's the square root of x squared? Okay. No reason that there's like 37 of you and one person can answer that. Can you pay attention or should I just like let you practice and then move on with my life? So square root of x squared is what? Square root of 16 is what? 4. And then the middle term is always 2 times the square roots of your first and your last term. So 2 times x times 4 is 8x. And that's true for all of these. This is a perfect square. This is a perfect square. What's the square root of x? Or sorry, x squared? What's the square root of 1? What times what equals 1? So the square root of 1 is 1, and then if we follow this rule down here and times that by 2, we do get the middle term. Same thing down here. All right, personally, I don't like memorizing that, although it is like a true fact, and it would make it easy to identify when it's in standard form. Personally, for me, I would just factor it, like how we've been doing. And I would think, what multiplies to 16 and adds to 8? 4 and 4. And because it happens to be the same exact number all the way down to the symbol and everything, I know that when I write it in factor form, it's gonna be considered a perfect square. Because it's the same exact thing multiplied by itself. All right, questions on that? Okay, so then now to like the meat and bones of our lesson, so that all was review. I want to hear like that. You know what's going on, we go over it over and over again. Now you need to be able to explain why these are perfect squares. And that could be from following that rule we just talked about. That could be from you factoring and showing that the factor form is a perfect square. But be able to explain why all of these are perfect squares, do the factor form of it if you can. And write a definition for yourself for what perfect squares are in that blank space. Give you 3 minutes to do that. Prove that x squared plus 6x plus 9 is a perfect square. Wait, sorry, one more time. X times 4 x times 6 times 3, like what are you doing with these? Oh, okay. So I think she's going off of what we learned from the last activity, which is that perfect square trinomials go in this format. And I reversed the n and the x right here, but same difference. So if this is a perfect square trinomial, you have a perfect square here, which it is, a perfect square there, which it is. And then that middle term is always your square roots and then times 2. Order doesn't really matter, multiplication, so you can put it in the order that you want. X times 2 times 3 is 6x, and these are both perfect squares. So that does follow the format that we learned in the last one. However, I like just memorizing fewer things, so if you're like, what the heck are you talking about? Hopefully you know how to factor a trinomial. You set up your diamond like this. You think of two numbers that multiply to 9 and add to 6. So what two numbers multiply to 9 and add to 6? And then because that's the same exact number, my parentheses will look the same when I do write it out. And it's easier, in my opinion, to see that it's a perfect square when it's in fact good form. So that's another way. Table 9, why is the middle one a perfect square? Could you factor it maybe? Table 9, how do I factor a trinomial? What method do I use? Okay, so if I was setting it up for this problem, what would have to go on the top? And what would have to go on the bottom? A negative 16, so always keep a sign that's in front of it. Class what multiplies to 64, but adds to negative 16. Negative 8 and negative 8. So it would have to be the same sign to multiply to a positive. And to add to a negative, they both have to be negative. So it ends up looking like this, which really means I could write it like this and kind of condense it. That can be your proof why it is a perfect square. Okay, now the last one, I know some of you will look at a problem with fractions and just skip it and just like, take the L on it. You will have a problem like this on your final. Like you will, it'll be fractions. And you don't, like, my job isn't to teach you necessarily all the fraction rules and test you on all the fraction rules. You could just use a calculator for those parts. But still, like, you can set up a diamond and see, does it give me the same two numbers that multiply to the top and add to the bottom? So I'm gonna set up the diamond. It'd have to be 1/36 on the top, 1/3 on the bottom, and actually, let me maximize it for a second. Ignore the having to add to 1/3. Just think about if we're trying to see if this is a perfect square, I need the same number to go here and here. When we multiply fractions, we really just multiply them straight across. So what times what will give me 1? So 1 times 1. And then, because we're wanting it to be the same fraction that fills us up, what times what will give me 36? So if I fill in this diamond with 1/6, I know that multiplies to the top. See if it adds to the bottom, and you can even use your calculator for that. Probably not your phone calculator unless you have it specifically on Desmos. But all other like scientific calculators, graphic calculators can do this for you. I know adding and subtracting fractions is annoying, so you need to have the same denominator. But if you use your calculator, you can see the decimal, and then if you press this button, you can see the simplified fraction. So it does add to 1/3. So my factor form would look like this. X plus 1/6 in parentheses squared. Or you can expand it if you want, but because it's the same number that is making the diamond work, then that makes it a perfect square. Okay, good, any questions? So you could fill in your own definition for perfect squares. Something times itself is a perfect square. You draw an example, you do need to move on to the next side. So identifying them is one of the skills you'll be tested on. The other skill is going to be solving when there's perfect squares. So Han and Jada solve the same equation with different methods. Han's method we've done before. So this you've seen before, hopefully you know how to do it. If this is my given problem, here he is expanding it, setting it to equal 0, or actually now he's actually FOILing to get the standard form. Setting it to equal 0 by subtracting 25 on each side, factoring. So multiplying to -11, adding to -12, which means -11, -1. And then using your zero product property. So that's a long process, as you can see. So we learned how to do each step of this. Now compare it to Jada's. Hers is way fewer steps, isn't it? And she got the same answers. So if you notice that you have perfect squares on each side, like that's a perfect square. 25 is a perfect square, which is square root of 25. So if you notice that, it does make it a little bit easier to solve. You're basically just isolating x at that. So what's the opposite of squaring? And whatever you do on one side. So that cancels out squaring on the left side. That's why it becomes x minus 6 on the left. And like we said, the square root of 25 is 5, but don't forget, it could also be -5. So moving forward, when you square root, you have the positive and negative case that you need to solve for. That's why after this step, it splits into 2, where she's solving for the positive 5s and for when it's equal to -5. What's opposite of minusing 6? And whatever you go on one side. And she separated it completely out. You could do that if that's easier for you. I just remember like the plus and minus sign, I just have to do it twice. So like what's +5 plus 6? 11. What's -5 plus 6? 1. All right, but here it's showing you could do the same thing here, add 6 to each side, solve them separately and get the same. Questions on that? So Han's method we've already done. I would like you to practice these problems, solving for your zeros, your solutions, using Jada's method. If I'd like split it up between you guys, I want you practicing this other method, not the same method we've been practicing for the past like 5 lessons. Use Jada's method, which is shown here, to solve things like these 3 problems. Maybe 5 minutes. Kayla? Okay, 12 and 2. Anyone get something other than those? Harley? 12 and -2. Anything other than those? Ooh. Okay. So let's start there. So we have a difference in answer, so we should probably check that one out to see whether it should be 12 and 2 or 12 and -2. So the only time you can use Jada's method is if you have perfect squares on each side of the equal sign, like nothing else extra, just perfect squares on each side. So I know this is a perfect square because it's an expression squared, so that's easy. Is 49 a perfect square? Yes, and because so many of you are not answering, just want to remind you, you can check that any number is a perfect square if you can put it under the square root symbol. And it gives you like a whole number. Usually people have the first 12 perfect squares memorized. Like the answer for 1 square, 2 square, 3 square, 4 square. But, you know, you always test it out and see. But there are perfect squares here, so I can use Jada's method. What's opposite of squaring something? Whatever you do on one side of the equal sign, you do to the other side to keep it equal. So that gets the y minus 5 alone. Square root of 49 is plus or minus what? And don't forget, you have to solve for both cases. That's why we put plus or minus now. What's opposite of subtracting 5? Whatever you do on one side. And if you want to do what Jada did and made it 2 separate problems to solve, that's fine. I like to save room, especially when I'm only working with this much room. So just remember to solve for both cases with the plus and minus sign. What is positive 7 plus 5? And what is negative 7 plus 5? So it should be the -2 as the other 0. But otherwise good. Way fewer steps than like expanding it, multiplying it out, setting it equal to 0. While that works better in some cases, the factoring, when it looks like this, it might be easier to just do this. Did anyone get answers for the second one? Harley? That does sound right, if I remember correctly. So there has to be perfect squares on each side, and there are. So you can isolate the x or start isolating the x by taking the square root of both sides. What's the square root of 9? And don't forget plus or minus 3. Just start saying it in your answers now. The calculator will only tell you the positive, but really there's 2 every time it's square root. Opposite of adding 4 is whatever you do on one side. And don't forget to solve for both cases. What is positive 3 minus 4? Good. What's negative 3 minus 4? Good, so that is correct. And then I don't think we have time to fully walk you through the last one. Anyone have that one, you think? Harley? And that is correct. Because I remember it from earlier. So again, you square root both sides. That makes it y minus 0.1. And the square root of 0.36 is plus or minus 0.26. Yes, that's correct. So no, 0.06. No, 0.6 is right. Okay, anyway. Add 0.1 on each side. And then don't forget to solve for both cases. So positive 0.6 plus 0.1 is the 0.7. Negative 0.6 plus 0.1 is where the negative 0.5.